Hi, this is Kenny Lee. In this video, we're going to talk about how to calculate the speed of sound and how to use that with the other wave equations to calculate different values. So, sound is a longitudinal wave. And so that means it's got compressions, rarefactions, compressions, refractions. So one molecule has to bump into another molecule, which bumps into the next molecule, which bumps into the next molecule. And so that propagates the sound wave. So there are certain conditions that could affect how quickly that movement happens. And one of them is temperature. The warmer the air, the faster the sound will move. The colder the air, the slower the sound will move because the molecules will be moving slower. The air is warmer, the molecules are moving faster, so they can cover that distance quicker. So for us, we're going to use this, that the velocity of sound in air, this is only in air, not in water, not in solids, just in air, is 330 meters per second plus an additional 0.6 meters per second for every degree Celsius. So for the first one, we're going to calculate the speed of sound in 30 degrees Celsius air. Oh, by the way, we're going to use 330 meters per second. You may see the same equation, but instead of 330, they may have 332 or something like that. That usually is determined by the location that you're at. For us, we're going to go ahead and just use 330. So what's the speed of sound in 30 degrees Celsius air? Well, it's really easy. Velocity of sound will be 330 plus 0.6 times the degrees Celsius. And so in this case, it would be 330 plus 0.6 times 30 degrees. And so 30 times 0.6 gives us 18. And so the velocity of sound will be 348 meters per second at that temperature. Now that's easy enough, but let's mix it into the equations that we already know. Since sound is still a wave, it still follows the wave equation and this relationship between period and frequency. So if we get a problem like this, where we have a 256 hertz tuning fork, played in a room that has a temperature of 30 degrees Celsius, what's the period and wavelength of the wave? All right, so hertz, that's the frequency. So our frequency is 256 hertz. We have a temperature of 30 degrees Celsius. And we want to know the period and the wavelength of that wave. Okay, so the first thing is I've got a sound wave because it's coming off a tuning fork, and I got a temperature. So the very first thing I want to do is figure out the speed of sound at that temperature. So 330 plus 0.6 times degrees Celsius. So it'll be 330 plus 0.6 times 30. This is just like the last equation. And we still get 348 meters per second is the speed of sound at that temperature. Now, since we know that, we can do a couple different things. I can actually figure out period directly, but I want to do this. I actually want to figure out wavelength. Since I know the velocity, we might as well do that because we know velocity equals wavelength times frequency. Velocity is 348. The wavelength we don't know, but the frequency is 256. So we're going to take that 348 and divide by 256, and we get a wavelength of 1.3, let's call it 6 meters. Now to figure out the period, we just use that relationship. Period is equal to 1 over frequency. So period will be 1 over 256. So 1 divided by 256 gives me a period of 3.9 times 10 to the minus 3 seconds, or if we write it out, it's 0.0039 seconds. Either one would be fine. Okay, let's try another one just for the sake of practice. All right, this time we're given the period of the wave and the temperature, and I want the frequency and wavelength. Okay, so I'm given the period, 0.005 seconds. I'm given the temperature. It is a sound wave, so temperature matters. Now, if this was a beam of light, then it really wouldn't matter what the temperature is. That has no effect on light. But for sound, the temperature will matter. And we're looking for the frequency and the wavelength. Well, since I know the period, I can go ahead and figure out the frequency. Period is 0.005 equals 1 over the frequency. Super secret metric, you go ahead and swap those out. Frequency is 1 over 0.005. And so we take 0.005, take the inverse of that, we get a frequency of 200 hertz. Now that we got that, we can figure out the wavelength, because we have velocity equals 330 plus 0.6 times degrees Celsius, because we still have to deal with that temperature. So we got 330 plus 0.6 times 22 in this case. So 22 times 0.6 plus 330 gives me a speed of sound of 343.2 meters per second. This is why musicians usually have to retune their instruments if they go from one location to the other, because if the room temperature is different, or maybe even the altitude's different, the speed sound travels in that air is different, so they have to retune their instrument so that it plays the same frequency. But in this case, we're looking for wavelength. We already know the frequency is 200. So velocity equals wavelength times frequency. 343.2 equals wavelength, which we don't know, and frequency is 200. So we take 343.2 and divide by 200, and we get a wavelength of 1.7, let's call it 2 meters. Now this is all using the wave equation where I'm looking for a frequency, a wavelength, a period, something like that. But there is a different type of question that uses sound waves. And that's this one. We've got an iceberg that's 20,000 meters away from a boat. Their temperature is that, and they're asked for how long will it take people to hear the echo. All right, so let's sketch things out for this one. So there's my water, there's my iceberg, here's my boat. And the iceberg is 20,000 meters away. So I've got an air temperature. So first thing I want to do is figure out the speed of sound at that air temperature. So 330 plus 0.6 times degrees Celsius. So 330 plus 0.6 times negative 15. So 0.6 times negative 15, which is negative 9, so we get 330 minus 9, so that's 321 meters per second is the speed of sound at that temperature. But we want to know how long would it take the people to hear the echo. Now that is important because that means the sound has to go out to the iceberg. And if we just want to know that distance or that time, we just use this distance here. But that sound in this one is an echo, so that means the sound has to come back. So that really means that that sound wave traveled 40,000 meters to get to the iceberg and back. If we only want to know to the iceberg, 20,000 meters is fine. But this sound went out and back, so we had to double that. And in this case, we're not going to be able to use the wave equation because we're not looking for a frequency or wavelength. We're actually looking for a time, which is different. So we're going to go all the way back and use this equation. Velocity equals distance divided by time. Velocity was 321. Distance is 40,000 meters. And we got to figure out time. Again, supersecret metric. Time comes out. And the 321 takes its place. So 40,000 divided by 321 gives me a time of 124.6 seconds. Well, it'd take nearly 2 minutes, or a little more than 2 minutes, for that sound to go out and come back. Pretty far away. All right, let's try another one. All right, on this one, we actually do want to know the distance. And we got an air temperature again. So we've got a person standing in front of a cliff. They yell. It takes 3 seconds for them to hear the echo. Okay, now this is important. And we want to know how far away the cliff is. So time is 3 seconds to go out and back. So to just go out to the cliff wall should be just half that amount. So the actual time to get out to the wall is 1.5 seconds. Now that we've done that, we can start figuring things out. But first, again, since it's sound in an air that has a temperature, we need to figure out the velocity of sound at that temperature. 0.6 times degrees Celsius. So 330 plus 0.6 times the temperature, which is 25 degrees. So 0.6 times 25 plus 330 gives me 345 meters per second is the velocity of sound. And again, this one is not asking for a wavelength, a frequency, a period. It's asking for a distance. So we're going to use velocity equals distance divided by time. Velocity is 345. Distance we don't know, but the time is 1.5 seconds. So 345 times 1.5 gives me a distance of 517.5 meters from that person out to the wall. Okay, let's sum things up a little bit. Okay, in summary, the speed of sound in air is dependent on the temperature. The warmer the air, the faster it goes. The colder the air, the slower it goes. But it's all governed by this equation, and we're going to use 330 plus 0.6 times degrees Celsius. Since sound is a wave, the wave equation and the period frequency relationship still works. We can still do this if we're looking for wavelength or frequency. If I got the period or frequency, I simply take the inverse to get the other one. But I can't forget that there are some questions where we just want to know how far out something is, or how long it takes an echo to go there and come back. And so in those cases where we're looking for more of a distance and a time rather than a wavelength or a period or frequency, we're going to go back all the way to V equals D over T and solve for whatever we need to. All right? Good luck on solving problems, and I'll talk to you later. Bye.